Bismillahirrahmanirrahim. This is Electric Circuits course of second semester students, and this semester is offered in spring 2020. This is our textbook, and I am Dr. Khalid M. Hassan in the Department of Electrical Engineering. In this lecture, we'll discuss chapter 8 on sinusoidal steady-state response. Note that only first two sections of this chapter are included in this course. This is part 1 of the lectures, and in part 1 sinusoid and phasors will be discussed, and in part 2 we'll start discussing phasor circuit analysis or electric circuit analysis using phasors. Now the phasor representation. The phasor concept is the foundation for the analysis of linear circuits in sinusoidal steady state. Note that we use phasor representation to analyze linear circuits to find their sinusoidal steady state response. Sinusoidal steady state response, this is important. When a linear circuit is powered by or excited by a sinusoidal voltage or current source, we find its sinusoidal steady state response using phasor representation. In the previous chapter on first order circuits, which was discussed in chapter number 7, we found both the transient and steady state response. But in phasor analysis, we find only sinusoidal steady state response. Phasor is a complex number representing the amplitude and phase angle of a sinusoidal voltage or current. The connection between sine wave and complex number is provided by Euler's representation. Note that you should pronounce this as Euler's, a famous mathematician. This is Euler's relationship. E raised to the power j theta is cosine theta plus j sine theta, and you know this due to your college mathematics. Complex number representation, cosine theta plus j sine theta, and this is represented by Euler's relationship as Ej theta. Now in this, this is the real part. Cosine is real part of Ej theta, and sine is the imaginary part of Ej theta. Now, how we represent a sinusoidal voltage Vt, which is expressed in time, how we represent it in phasors, in the form of phasor. The choice between the two includes involves deciding whether to describe the sine wave using a sine or cosine function. Now, in Euler's representation, Ej theta, it is sum of sine theta plus j sine theta. So the cosine theta is the real part and sine theta is the imaginary part. Now we have to choose cosine theta or sine theta in order to represent the voltage, and this choice is ours. We chose cosine function as it will facilitate our further calculations and analysis. So we choose the real part, which is cosine theta, in order to represent a voltage expressed in time domain. Now in it, say this is the voltage, a sinusoidal voltage. Note that cosine is also sinusoid, and cosine is a time shifted form of sinusoid. If we shift the sinusoid, if we origin the shift of a sinusoidal function of waveform to positive side by pi by 2, it becomes cosine. It means that sine omega t plus 90 degree is a cosine function. And we can represent cosine as sine or sine as cosine. So proceeding further, VA cosine omega t plus phi. So as cosine is the real part of EJ omega t plus phi, and we can then show it separately as EJ omega t and EJ phi. This part EJ phi, it represents the phi, which is the phase angle, and EJ omega t, it represents the frequency omega. Now we proceed further and we combine VA EJ phi together and EJ omega t, and this quantity VA, product of VA and EJ phi, is represented now with a bold case letter V, and this is the phasor voltage. This part is the phasor voltage, and this phasor voltage, as from this expression, is represented in a polar form as VAG phi, and in rectangular form VA cosine phi plus JVA sine phi. Sometimes we need to represent it in a rectangular form when we want to add or subtract two phasors. In order to, when we need to multiply two phasor voltage, say V1 plus V2 in the form of phasors, we may not need to represent it in a rectangular form. We can proceed further with this representation. So if we multiply two phasors, say V1 is VA1 EJ phi multiplied by VA2 into EJ phi 2. So we just multiply the magnitudes and we add these angles, and you may be able to recall your college mathematics. Now, this phasor is shown over here. This is the pictorial form of a phasor, and V is the magnitude, VA is the phasor shown with the arrow, and V is the magnitude, means the length of this arrow, and phi is the angle. This angle may be positive. Note that in electrical engineering, counterclockwise angles are considered as positive and clockwise angles are considered as negative. So this angle may be negative, may be positive. Note that the two components of this phasor V, vertical component is the imaginary part and horizontal component is the real part. In this representation, the phasor V is a complex number determined by the amplitude and phase angle of the sinusoid. Now, how we convert sinusoid to phasors, means how we convert voltage or current which is expressed in time domain as a sine or cosine functions to phasor representation. In phasor representation, we have two forms, polar or rectangular. Sometimes we need polar, sometimes we need rectangular. Say for example, we have a cosine function with omega, which is the angular frequency in radians per second. This is 150 radians per second, and you know that omega is 2 pi f, where f is the frequency in hertz. So 20 is the peak value, minus 60 is the phase angle. We represent it due to the magnitude. We use only the magnitude and we use only the angle, the phase angle. So you know only 20, the magnitude 20 is shown over here in phasor representation, and the angle. This is the polar representation. And in rectangular representation, uh, we expand it. It is 20 cosine of minus 60 plus j 20 sine of minus 60. So this is rectangular form. Similarly, this is another voltage in time domain. It's a cosine function, and we use its peak value, which is 10, as a magnitude over here, and the phase angle 180, which is over here. And in order to represent this convert this polar form to rectangular form, so we use 10 cosine of 180 plus j 10 sine of 180, which is over here. And similarly, a current may be expressed as a sum of two parts. So this may be I1, this may be I2. So how we represent it in phasors, in polar form and in rectangular form, I hope you should be able to proceed it further. So we express this as a in phasor form. This will be represented as using its peak value or the magnitude, and the angle, phase angle, which is 0, and this is the peak value, and here in phasors this will be the magnitude, and minus 90 degree is the phase angle. And in phasor representation, there is no information of omega. Angular frequency information is not visible. It is not included in phasors. There is no information of the frequency. So this frequency information is not included in it. To show the frequency, we use V. V is the phasor representation multiplied by E j omega t, and this product is a complex exponential, which is also called a rotating phasor, and we use arrow over here as if this, which is a complex quantity, this phasor is rotating at the frequency of omega. The phasor V is viewed as a snapshot of the rotating phasor at t equal to 0. Means if we consider this, R this, so say this 120 magnitude, and at t equal to 0, its angle is minus 60. So it will be shown over here minus 60. Look at the cursor here. This is minus 60, almost minus 60 angle, and the length is according to the magnitude, whatever scale we use. So it will be in this direction with the angle minus 60 over here, and this will be a snapshot of rotating phasor at t equal to 0. Conversion of phasors to sinusoid. In order to convert phasors to sinusoid, we must know the frequency, because in phasors there is no information of frequency. So this is phasor. As such, in phasors, no frequency information is included. So we must know the frequency. Frequency may be given in hertz or may be given in radians per second. Here it is in hertz, but in time domain we use radians per second. The frequency in radians per second, and you know that here we need omega, and omega is 2 pi f, which is 60 over here. And if we represent this in sinusoidal form, the peak value will be 169. So it will be 169 cosine omega t. Omega is 2 pi f and minus 45, which you can see over here. 169 over here. And cosine, we have chosen cosine as a function for phasor representation. And this 377 is 2 pi times 60, and this minus 45 is shown here. Similarly, this is another phasor voltage, and this phasor voltage is sum of two parts over here. This is phasor 1, this is phasor 2, and this is 10 with angle 90, and it is in a polar form, and this is in rectangular form. So we expand it, we represent it in a rectangular form, which is 10 cosine 90 plus j 10 sine 90. We then add real part of both and imaginary part of both, and we show it. Okay, I have shown it over here. 10 cosine 90 plus j 10 sine 90, 10 is common over here, plus 60, this is already in a rectangular form. So this part due to cosine of 90 is 0, and this part due to sine of 90 is 10. Note that 10 is common over here. Then we add 60 and 0, real part 66 and 0, and j10 minus j10, which is 0 over here, and this can be represented as the imaginary part is 0. If imaginary part is 0, the angle is 0, so it is 66 angle 0. So we show it over here, 66 and angle 0, and this is omega 10 raised to the power 4. Here omega is given directly as 10 kilo radians per second. This is 10 kilo radians per second. Similarly, do it by yourself for this current represented in phases. So how to convert this in time domain, you should do it by yourself. Now there are a few basic properties of phases. Number one is additive property. In time domain, if we want to add voltages of V1, V2, V3, it means voltage sources are connected in series. We add it like this. And in phasor representation, it is like this. It's a real part of V1. Note that V1 is the phasor representation of this V1, and this V1 will represent only the magnitude and the angle. So here V1, we don't know what is V1. Various forms of V1 are discussed in the previous slide. So as V1 is a real part of V1 Ej omega t and so on and so forth, and then Ej omega t is common in everything. Ej omega t is common, and this is the sum of all the phasors, and therefore sum of phasors, sum of these voltages in phasors form, this is the sum, is V1 plus V2 dot 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 plus Vn. Derivative property in time domain, the voltage is expressed as a real part of Ej omega t. We have discussed it before, and if we take d by dt, first order derivative of this, we have real part of j omega v, and note that this v is the phasor, and this is Ej omega t over here. This is due to rotation, we have included over here, but this bold case v is the phasor. Now proceed further. Note that in electrical engineering we use J instead of iota I, letter I, because we use letter I for current, and in order to just differentiate, we use letter J. J means iota. Now this j omega v is what is this part? This is the phasor j omega. Now this v, due to d by dt, due to differentiation, j omega is multiplied by v, or v is multiplied by j omega. This is due to the differentiation. Look at vt in normal form, real part of whatever is in the parenthesis, real part of whatever is in the parenthesis, Ej omega t, Ej omega t. Now v is over here, we see the coefficient of v as j omega. Now what is this j omega v? This is the differentiation of v e j omega t over here. Now omega, so what is j? J can be represented as EJ90. Expand it, EJ90 in a rectangular form. It is cosine 90 plus J sine 90. Cosine 90 is 0 and sine 90 is 1. Therefore, EJ90 is equal to J. And now proceed further, add this theta and 90 over here. So it means that due to the differentiation, we have a multiplicative factor of omega and additive factor in the phase angle of 90 degree. And we say that differentiating a sinusoid changes its amplitude by a multiplicative factor omega and a shift in the phase angle by 90 degree. This is the multiplicative factor and shift of angle. This is 90. It's a simple example how we add these two voltages. Voltages are represented in time domain. Note that we can directly add this V1 and V2 if we represent V1 as 10 cosine 1000t cosine 45 degree plus 10 sine 1000t sine 45 degree, and then similarly with this, and then we add sine with sine term and cosine with cosine term, and then we have the sum V1 plus V2. This is a direct method without using phasors, but how we can use it with how we can add these two using phasors. V1 is represented as now phasor properties of phasors. We use derivative property of phasors to find the time derivative of this. Note that we can differentiate this voltage expressed in time domain directly. We can differentiate it directly, but now we will use the derivative property of phasors, and in derivative property of phasors, the phasor representation of the original phasor voltage will be multiplied by omega, and the angle will be shifted by 90 degree, and you know it before. So this is J200. J means e raised to the power J90, means this is angle shift of 90 degree, and this 200 means the frequency over here. Now this voltage represented in phasors is 15 and only the angle. 15 and only the angle. This is the phasor representation of this voltage, and due to the derivative property, what is multiplied? It is multiplied by 200 omega, and this is the angle shift. J represents the angle shift, and our resulting function is 3000 angle 60. We add angle of 90 degree into it. Adding angle of 90 degree to it is minus 30 plus 90, resulting is 60 is the angle, and we multiply the whole with omega. So this is 15 multiplied by 2000, 200 is 3000. Now we can say that dV by dt is equal to this, and by differentiating it directly, go through this dV by dt is I have shown in this differentiation in each step how we proceed. Note that if we differentiate this voltage, which is represented in cosine, if we differentiate, we will have minus 15 into 200 sine, because d by dt of cosine function is a minus sine, so this is minus and this is sine. Now proceed further. Note that this minus and sine, we need cosine representation for phasors. So sine must be converted into cosine, or this sine function must be represented in cosine form. So we take this minus and sine, And we know that cosine of alpha plus 90 is cosine alpha, cosine 90 minus sine alpha, sine 90 as due to cosine 90, which is equal to 0, and sine 90 is 1. Therefore, cosine alpha plus 90 degree is equal to minus sine alpha. So minus sine, whatever is the argument, we consider it as alpha. So what do we do over here? dv by dt is 300. So we minus, shown in red, minus sine 200t minus 30 is represented in cosine as plus cosine 200t minus 30 plus 90 degree, and this is the overall result of this differentiation. And if we differentiate in time domain directly, we get 3000 cosine 200t plus 60. But if we represent it in phases, it will be 3000. We take only the magnitude 3000 and we take only the angle 60 degree, which is shown over here. So this is the phasor represent. So we can exploit this derivative property directly in phases. This was the recheck in time domain, differentiating the voltage function directly in time domain and then representing it in phasor. Now there are three circuit elements: resistance, inductors, and inductance or inductor, capacitance or capacitor. So first we take resistance. In resistance, we know that voltage across the resistance is R times the current flowing through it. Voltage across an inductor is L times d by dt of the current flowing through it. In case of capacitor, the current flowing through the capacitor is C times or multiplied by d by dt of the voltage across the capacitor. So we consider this resistor first in order to see how a resistor will be represented or can be represented in its phasor equivalent. So if we assume the resistance current as I cosine omega t plus phi, the phasor representation of this IR, note that for phasors we use bold case letters IR. There is no time information in it, and we take over here, this is the peak value over here as magnitude and only the phase angle phi, which is shown over here. And we proceed further. What is VR? VR is in phases. What is the voltage? Resistor voltage in phases form, it is the product of resistance and current. Resistance and current, same is in the phases. So the resistance and current, and this current in a phasor notation is IR, and we see that resistance current, phasor current flowing through the resistor from left to right, and the polarity of the voltage. We follow the passive sign convention as we have been using it in this circuit, and it was discussed in chapter number 1. So resistance in phasors is shown as like this. So if it is in time domain, this will be Vt and this will be It. And the voltage over here, the voltage is in phasor representation, and the current in phasor representation. Note that in the phasor representation of the current flowing through resistor, this is the angle, and in the phasor representation of voltage across the resistor, so it is only multiplied by R, and IR is same. So the angle over here, the angle or phase angle, both in the current and in the voltage is same. Therefore, this is IR, and the longer over here line, it shows VR if R is greater than 1. So IR and VR, we call that the phase angle of the current and the resistance of the voltage in a resistance is same. The phase angle is same. It may be positive angle, it may be 0, it may be negative. So phase angle is same. Here we see how inductor is represented in phasor form. In the inductor voltage is L times the first order derivative of the inductor current. Or in here we assume inductor current in time domain. This is the inductor current in time domain. This is the inductor voltage. And in phasor representation, inductor current IA and phi only, IA and phi only, either in this representation or in this representation. And this is just a repetition, differentiating a sinusoid. Differentiating this sinusoid will change its amplitude by a multiplicative factor by omega, and the angle shift in it by 90 degree. So as VL is L di by dt, L, so this is di, this is d by dt, this is the differentiation in phasors, so multiplied by omega, and this is the angle shift 90. Rearranging these terms, we have j omega L IA with ej phi. So this is just to show that this is the multiplicative factor and this is the change in the angle. So here, just as a quick reference, J. What is J? J is EJ 90, and because EJ 90 is cosine 90 plus J sine 90, cosine 90 is 0, sine 90 is 1, therefore EJ 90 is J. Now what is VL then? VL again represented over here. VL then, go through this. VL is omega L IA EJ phi plus 90 degree. And this is the passive sign convention. It's a current flowing from left to right, then the polarity of the voltage will be as shown. This is positive side, this is negative side. So inductor will be replaced by J omega L ohms. We will call it, this is the later when we will discuss the impedance and reactance, we will call it inductive reactance J omega L, and the units are ohms. And this is the phasor representation of IL and VL. Note that in IL it has magnitude IA. IL, this is the IL, the magnitude is IA, and the phase angle is phi. This is phi. And in the VL, the magnitude in the inductor voltage, the whole is omega L IA. Omega L IA is the magnitude of VL, and the angle will be 90 degree plus the angle of the current. So whatever is the angle of the current, 90 degree will be added into it. And we see that the phase angle between the current and the voltage in case of inductor is 90 degree. And in capacitor, we will see that it is minus 90 degree. So anyway, the inductor in phasor analysis, whenever we have a circuit, inductor in a circuit, we will replace the inductance L by J omega L. It will be discussed in the further. Now the third circuit element, which is the capacitor, and we'll see how capacitor is seen in how capacitor is represented in phasor form. If we assume capacitor voltage as VA cosine omega t plus phi, and IC, we already know IC is C times time derivative of the voltage across the capacitor, and phasor representation of capacitor voltage is VA and the phase angle phi. This is time domain representation. In its equivalent phasor representation, we just need the peak value over here as magnitude and phi as the phase angle, either in this representation or in this representation. So this is VC in bold case. So what is IC? IC is C multiplied by time derivative of the voltage. What is time derivative of voltage in phasors? If we use phasor representation, we then we see that due to the differentiative property, if we take its first order derivative, it will be multiplied by omega, and there will be a phase shift or phase angle of 90 degree in it. So whatever is the angle, we add 90 degree into it. Proceed further, we end up over here j omega c, we see. Now here we have IC, capacitor current, is equal to j omega Vc. Now what is Vc then? This Vc is equal to IC divided by j omega c. So you have seen Ohm's law, Vc is equal to Ri. So this is a resistance type thing, though we call it capacitive reactance over here. Further, we can express it in this form or in this form. I hope you should be able to understand this. J over here, 1 over j. So j is ej90, 1 over j is e minus j90. Here there is no j over here, so this j in the denominator is represented as e minus j90. Proceed further, you will see that this is the coefficient, and what is the angle over here? Phi minus 90. Phi minus 90. The capacitor, the voltage in phasor representation is phase shift is phi minus 90, and the representation of a capacitor in phasor form is as 1 over j omega c. Instead of c, I will write it over here. Instead of in a circuit analysis, we have seen that this is the capacitor represented in say in the units of farads. It's due to its capacitance. So we will replace this C representation with this 1 over j omega c, or this 1 over j omega c can also be written as minus j divide by omega c, minus j divide by omega c. So this is the only difference in phasor representation. But with this representation, as you will see in the following slides, we have great advantage of a quick analysis. We can analyze circuits quickly in phasor representations. Now, phasor circuit analysis. In circuit analysis, we have a circuit, and omega is 50 radians, and this is how we can find the equivalent impedance over here. You know how we can uh, find the equivalent resistance in case of when we have all circuits elements are resistances R1, R2, R3, R4, R5. We have seen it in chapter 4. So when we have capacitors and our inductors along with resistors, we find its equivalent impedance. Impedance because we have capacitance and resistance in addition to resistance, and impedance, it depends on the frequency, and we find Zn means equivalent impedance or impedance seen from. So it is just like parallel series combination. If this is say Z1 and this is Z2 and this series is Z3, how we proceed further? So we know that in phasor representation, the resistance remains resistance as such. There is no effect of frequency on the behavior of the resistance, and inductor is shown as j omega L. You know that inductive reactance, it is proportional to the directly proportional to the frequency, and capacitive reactance is inversely proportional to the frequency. And now we replace this 2 millifarad as minus j over omega c. So this is minus j over omega c. Omega is 50 and capacitor is 2. So do these calculations, and this is minus j over 10, minus j10, and this is j omega L, j omega L. So omega is 50 and inductance is 0.2 Henry, so it is 50 multiplied by 0.2 is 10. So, and the resistance over here, it remains same, resistance, it remains same in a phasor representation, and the capacitor is minus j divided by omega c. Use this frequency and the capacitance, and you will have minus c. So we call it Z1. So this Z1 is minus J10. We call the series combination over here R and C as Z2. So Z2 is 3 plus this, 3 plus J 1 over J omega C. And over here this is in phasor representation. You know how quickly we can add these two in phasor representation, 3 minus J2 over here. And the series combination of this is, let us call it Z3. It will be 8 plus J10, 8 plus J10. And then finally Z in is Z1 plus Z2, parallel combination of Z2 and Z3. Parallel combination of Z2 and Z3, substitute Z1, Z2, Z3 in it, and you will have Z in the input impedance. Circuit analysis using phasors is simple, but in the circuit analysis using phasors, we can find only the steady state response if the input voltage or current or the circuit excitation is sinusoidal. So this is a circuit, and we have two inductors and a capacitor. Though we can analyze it in a time domain, but we will use phasors representation in the analysis. I have taken this from the textbook. We can use mesh analysis in it. In the mesh analysis, you know, this is mesh A and mesh B. So writing mesh equation will be 50 times IA plus J100 IA, and then minus J50 multiplied by IA minus IB is equal to the voltage rise, Vs in it. And IB is 100 J100 IB plus 50 IB and minus J50 IB minus IA. Note that we can show it as minus J over omega C or 1 over J omega C. So we have to take it as such, minus J50. So we can use mesh analysis and two equations, mesh equation and this equation for the second mesh, and then we can solve these two equations in order to find IA and IB in phasors form, and then we can proceed further in order to see the voltage and voltage and voltage over voltage across each circuit element. We can use nodal analysis. In nodal analysis, you see in nodal analysis, we have to identify all nodes. So we have identified all nodes. This is the ground or reference node, and this is the supply voltage. And you know, in case of the supply voltage, if one end of the voltage source is connected to the ground and other end is a node, then the node voltage is directly shown over here. The node voltage over here is equal to Vs with respect to ground. So we need to write equation 1, 2 and 3. We need to write 3 equations, and we use the node analysis method we discussed in chapter, I think in chapter 3. So node equation at VA, current leaving and current leaving, VA minus VS divided by 50, VA minus VB divided by 100. We write second equation at this node, VB minus VA divided by this, VB minus 0 divided by minus J50 plus VB minus VC divided by J100, and at the end the node equation here, VC minus VB divided by this J100, VC minus 0 divided by 50, and we have 1, 2 and 3 equations, and we can solve these equations simultaneously in order to find VA, VB, VC. The concept of Thevenin equivalent is same as we have discussed in previous chapters. Chapter 3 means we may want to see the Thevenin equivalent of the whole circuit seen by this 50 ohm resistance or by any circuit element, the Thevenin equivalent of the rest of the circuit. We use same techniques and are the Norton equivalents. There is nothing new in Thevenin equivalent, in Norton equivalent, in nodal analysis, in mesh analysis, in phasors representation, or in phasor circuit analysis. Nothing is new in already learned or discussed circuit analysis methods. Uh, I have included this circuit in my lecture. So this is not first order circuit. So it is a third order circuit, 1, 2, and 3. Note that if more than one inductors are connected in parallel or more than one inductors are connected in series, it will be considered as one equivalent inductor. One equivalent inductor. So if more than one capacitors are connected in parallel, more than one capacitors are connected in series, we will consider it as one equivalent capacitance. Now, neither of these two inductors are in series nor in parallel. So we have energy storing element 1, energy storing element 2, energy storing element 3. So later you will learn that we can write mesh equation, we can write node equation directly in time domain, and it will be a third order differential equation, and we can solve third order differential equation directly in time domain. But solving, analyzing the circuit in phases is extremely easy as compared to analyzing it directly in time domain. So, though only first order circuits are included in this course, and I have just given you an example of second order, a third order circuit. This is end of part 1, and only two sections, 8.1 and 8.2, are included in this course.